Hello and welcome to another Developer Essentials video. So this time we're going to be looking at maths. And, you know, there's a good chance that if it's a maths one that people's immediate reaction to this is going to be, oh, please, no. And I get it. And that's because a lot of the times when we are taught maths, it is maths from a point of view that is really boring. We're learning it in the context of, okay, well, I've got 5 of this and I've got 10 of this, or this train is going in this direction and this one's going in this direction, and where are they going to hit? And it can be really hard to get excited about maths in that context. It's also, let's, feel for the poor teachers in that case trying to make maths exciting in that context. It's not easy. It's very hard to make maths exciting in contexts like that. I have it a bit easier with this in that the maths I'm going to be showing you is all in the context of games. And it is all about helping you do cooler and more interesting things in your games. That's my sales pitch. I really hope it's worked, that you're like, hell yeah, I totally want to learn about maths now because it's going to let me do cool things in games. And it will. I promise it will. And it's really useful knowing the maths there. It can allow us to find solutions that we might not have been aware of, and it can also allow us to find better solutions for things as well. So I'm going to start off, as always, with getting some folders set up. So in some of the later videos, I will hit a point where I don't show all of the setup stuff. This is still a case where at this early stage, I think it is useful to still see this initial sort of setup process. So I'm going to have 3 materials. One is going to be red, one is going to be green, and I feel like folks can probably guess that the other one is going to be blue. So we'll get those set up. So we've got blue, we've got a green, and we will have a red. Cool. So we've got our colors. I'm also going to set up a few cubes. So I'm going to have cube red, which, as the name suggests, is going to get the red material. I'm going to switch back to the scene view just so I can see it there. So I'm going to move this 3 meters to the left. And I'm going to set up cube green, which is going to be in the center. And with each of these, I'm going to show you a slightly different way of setting the material. So for the first one, I dragged it on into the hierarchy. In this case, I can drag it into materials. I don't want to actually remove that other one. Could have just dragged it into a specific slot. And then for the blue cube, I'm going to have that set up, and that, I'm going to drag that in here and position that there. So 3 cubes, because these are going to be doing different things. So there's a bunch of different sets of maths we're going to be looking at today. I'm also going to chuck in just a plane so we can see where those cubes are. I'm going to lower that plane a little bit so they're sitting on top of it like that. Perfect. So let's start to look at the different things. So I'm going to set up an initial script that is going to be vector demo. So a common thing that we will be making use of in Unity is something called a vector. And we have already seen in some of the earlier videos we're making use of a vector 3. And there's also other versions of that, like a vector 2 and a vector 4. But we're going to have a look at what a vector actually is. So we've seen it, we've used it in the context of position. But a vector has a very specific meaning. So a vector has a direction and it has a magnitude. Now, when we see it typically in Unity, what we are seeing here is we see these x, y, and z components of the vector. And that actually is defining a direction and a magnitude. So vectors actually point in a particular direction. So what I'm going to do is in my vector demo here, I am going to set up, so I have a vector 3, and I'm going to call this my debug line vector. And what I'm going to initially set this to is vector3.up. So that should be a vector that is pointing in the upwards direction. So this is the vector for that. And then what I'm going to do is in update, I'm going to say debug draw, and I'm going to use this draw, actually I will use draw line. So I'm going to draw a vector that goes from my current position to my current position plus that debug, transform position plus the debug line vector. And I want that to be, do I have magenta? I do, good old magenta. Draw the debug line vector. So, okay, that will let us see what we actually are having happen here. And this will, I'm going to actually bring the game view down to here so we can focus on the scene view. So if I run this, then we can see we've got our lines being drawn there. And I'm going to pick the blue one here. And so as I change the value here, I'm changing the direction this vector is pointing in. So it's got different directions in each case as I move this. It's also changing the length of it because the height isn't changing. So it's still pointing to a point that's up here at the exact same height. So that height isn't changing, but the length of the vector, what we'd call its magnitude, is changing. So vectors have a direction and they have a magnitude. So as I'm changing this component, I'm changing its magnitude as well as its direction. Let's split those out a little bit though, and let's make it that what I'm controlling here is the magnitude as a separate thing and see how that looks differently. So public float debug line magnitude. And let's start that at 1. So to incorporate that debug line magnitude, that's going to give us a way of changing the length of it. So in this case, I won't change that vector. So the direction is going to stay the same, but I will change the magnitude of it. Once that runs, then we'll be able to see, so magnitude, I can scale that up or down, so I can change the size of the magnitude of the vector. So vectors have a direction, so where they point, and they also have a magnitude. But as we saw, these are all using the same vector, and it is the exact same vector. We've got the same direction, same magnitude for all of them, but they're at different locations. So that's because a vector doesn't have a point that it applies at. A vector, you can apply it at any point. So it means that this cube, doesn't matter where it is in the world, I can apply the exact same vector and it will result in the same behavior. So it will offset it by a certain amount in this case. So vectors have a direction and they have a magnitude, but they don't actually have a origin point that they apply at. So let's start doing more with this. Let's start doing something where, that's okay. But what if I actually want to, have stuff where I want to make the object move. So that was drawing my debug lines. I'm going to turn that off. I'm going to turn off this section of code here so it doesn't get grumpy at me. So what I want to be able to do is I want to have something where I want to be able to control the direction. So movement, direction. And I might want to say that these all can move up. But then I might want to also control the movement distance. And I'm going to initially set that to 1. So what I want to do then is move the object. So it'll be transform.position plus equals my movement direction times by my movement distance. Now I'm going to do an extra little check here. I'm going to do something where I want to actually check how much did it really move. So to do that, I'm going to store my previous position. And that is going to be my transform.position. So I'm storing the previous position. I've got my previous location. And then I'm going to calculate how far we actually moved. And there's a handy way of doing that. So distance moved, I can say is vector3.distance, and I give it 2 locations. So I give it my previous position and my current one. Because what I want to have happen is, regardless of what I set movement distance or direction to, that movement distance always matches distance moved. Because then I can be saying that we expected to move movement distance, actually moved movement distance. That's what I want to be able to, and what I should see, and it would help if I have the correct variables there, I should expect to see these two match. Now, if you have done some vector maths before, then you might be able to think of a scenario where they won't actually match because there is a problem with what I've written. Now, it doesn't show up at the moment. That looks fine. If I make it that green is moving 1.5 and red, let's say, make that move 0.5. So we've got a few different values, and let's check and see, okay, well, it's still working correctly. Now let's change the direction that it moves. So red can stay with moving directly up. Green, I'm going to say that the direction it moves is not just 1 in y, but also 1 in x. It's moving a diagonal. So I want it to move 1 in y, 1 in x, so it should be moving up towards the top left. I'm going to say for blue, I want it to be moving in all directions. So blue, I want it to be moving it essentially back towards me and up. So let's see what these say in terms of the distance, because all of them, it's saying still move 1 unit. But they haven't actually moved that amount. And this is an important thing that we run into. And we can see, the green one has moved quite a large distance. Green was supposed to be moving 1.5, but it actually has moved 2.1. So they've moved quite a bit more than they were meant to. And that's because when we're working with directions, so when we're using a vector to actually move something just based on a direction, what we typically need to do is, because what ends up happening, the maths that happens behind the scenes here, is it takes the position, so 0, 0, 0, and then it will take 1 in x times it by 1.5 and add it to this. And we can see, if we look at the values, it's gone to 1.5, 1.5. So when we're doing this maths, we're saying, okay, distance times by that value, times by that value, times by that, and we add each one. So we're working with x, y, and z separately. So that's not going to move it exactly the right distance, because this needs to be, this doesn't have a magnitude of 1. And if we can actually see that. So the magnitude, when we're using something as a direction, we want its magnitude to be 1. We want it to be what's called a unit vector. So we can actually look and see the movement direction magnitude is, and we can ask for this information. So we can say movement direction dot magnitude. And what we will see is for the one where it does actually match, the magnitude is 1, whereas for the ones where it doesn't, the magnitude is something other than 1. So we can see, expected to move 1, but we actually moved 1.73, so the same as the magnitude. Magnitude in this case is 1.4, expected to move 1.5, but we actually moved further. So those magnitudes are, and we would find that the scale there corresponds. So we need to be bringing that magnitude down to be 1. So we can do that. We can say movement direction dot normalized. That will, so when we normalize a vector, we preserve its direction. So its direction stays exactly the same, but we make the magnitude of that vector 1. What that allows us to do is very then carefully controlled distance. Because if whatever we multiply that by, that's the distance we will move. Because we'll see now, these end up in slightly different locations, but we can see, move 1, actually move 0.999, essentially as close to 1 as we can represent. Expected to move 1.5, actually moved 1.5. So when we're working with vectors, we need to remember they have a direction and they have a magnitude. When we're using those vectors for doing things like movement, working with stuff like speed, then those vectors need to be normalized for that direction. If they're not, then what happens is we get a scaling up, or potentially, depending on the values, a scaling down that is happening there. So we need to always make sure when we're working with vectors that we are normalizing if we are using those in something where we're moving by a distance, stuff like of that. So if we just want the direction from a vector, we normalize it. So vectors, we know they have a direction and a magnitude. We know that we need to normalize that direction if we're wanting to use it for then scaling it by a distance, something like of that. We can add vectors. When we add vectors, we add the individual components. So we do x plus x, y plus y, z plus z. So we add the individual components there. We can't multiply or divide vectors by each other. That's not a thing that's possible. But we can scale them. And that's a very common thing that we're doing. We might also need a vector to point in a particular direction, to point at a particular thing. And that is something that we can actually do. So what I am going to do is I'm going to set up something where we have an object move towards another object. So I'm going to create a sphere, and this sphere I'm going to position it initially at, that's a pretty good spot. Let's make that at 9 of 10. So I want this sphere to move towards the plane. That means that sphere needs to have a vector to the plane. So I'm going to set up a script that is going to be move to target. And this script is going to go on the sphere. So the sphere is set up here. So this is going to show a couple of things that we haven't really looked at yet, but that's okay. There's going to be other videos coming up that will allow you to see this stuff. So I'm going to need to have a way of keeping track of my target, and I'm using just the transform, because transform has the position, and that's the only information I need. If I'm moving towards something, I probably need the speed. So how fast I want to move towards it. So speed, I'm going to initially set that to be 1 meter a second. So what I am going to do then, now this I'm going to design it so that it can work for a target that was moving. If it was a static target, I could move some of this logic into start. In this case, I'm going to assume it's a moving target, so I'm going to do this in update. So first thing is, I need my direction. So to get my direction, this is how we always do it with a vector. So if we want a vector, so to get a vector that points from A to B, we take the position of B and subtract the position of A. So to get the vector to that target, direction to target, it's the target position minus our position. That gives us a vector towards that target. So then to move towards the target, what we do is we would say R transform position. We are going to add to that direction to target multiplied by our speed. And because we want to be able to have this work nicely with speed, we're also going to multiply that by delta time, so how long it's been since the last update. So what this will do is it will move in this direction. So we've got our vector that says which way to move. We also have our speed for how quickly we want to move there. And we are multiplying the speed by how long it's been since the last update. So we're getting the actual amount of distance we could have moved. So if we're moving at 5 meters a second, this says, well, how many seconds has it been? And it multiplies those two. So 5 meters a second times the amount of time it's been. Okay, you're allowed to move 10 centimeters. So it says move 10 centimeters then towards that target, for example. Now I have intentionally missed something. I have missed normalizing. That is deliberate, because I want to show you what happens when you're dealing with movement if we don't normalize stuff. So we've got our move to target. We need to say that the plane is the target. And then let's run it and see what happens. So I haven't normalized it. And so you notice how it slows down. And that can actually be a thing that you might want. But we see it moves really rapidly. And if we go frame by frame, we can actually see that even more clearly. So if you pause and then hit play, it lets you go frame by frame. And we can see it's moving quite big jumps initially. But what we'll see is those jumps actually, we're only a few frames into it. That's why it jumps really quickly. When we unpause, it then starts to slow down. So it doesn't move at a constant speed. If we normalized our direction to target, which I'll actually do the normalization here, dot normalized, we will see that it now moves at a constant speed. So we run it, and it's a very constant, even speed. We know exactly the velocity that it's moving at. And that's the thing that will happen. If it's not normalized, the farther away it is, the faster it actually will move initially, because that vector is huge. And as we get closer, that vector gets smaller, which means we slow down. So it can be a deliberate thing that you could do in a case like of this, where you want the object to be moving rapidly and then decelerating. So it can be a deliberate thing, but it's something where if you're doing that, keep in mind that this is how it behaves. If we don't normalize, it will actually slow down as it gets closer towards the target. And so this is an easy thing to run into if you forget to normalize, and you can notice some really odd behaviors happening there. So it's just something to watch out for there with that. So, okay, that's cool. We've seen things that we can do with vectors. We can construct a vector to a particular location. We can see how we can scale them. We can use a vector for having something move towards a target. And the advantage with this is if I get this and then my plane, if I move my plane, it's always going to be moving towards it. That was what I was saying with doing this in update rather than doing this in the start. It's able to adapt to wherever the object is. So it means I can make it that it can't ever catch it. So that's a handy way if you're wanting to have something that's like a seeking projectile or something like that. You could use the process there of moving toward calculating the vector in update and just always moving towards that. But let's do more than this, because we've seen, vector maths is going to be one of the really common ones that we do make a lot of use of. It's an area that we're continually using it. There are other areas of maths that we can make use of that are good to see as well. So we've previously seen a bounce script. I've done a bounce script where it was using an animation curve. Let's now look at a bounce version 2. So this is going to be something, I'm just going to put this on the, let the green one bounce initially. So the bounce script, previously we used an animation curve. Now we're going to use trigonometry. So the main cases where I use sine and cosine functions in a game is actually for having bits of movement, for having stuff bob up and down. You can use them for when you are solving particular maths problems, and those are ones that we will have a look at that, but we will have a look at that at a point in time where we've got one of those particular problems. It's not a set of code that we're often running into. It's actually very rare that we're running into stuff like that. But using sine and cosine and being aware of them is a really handy thing for setting stuff up. So again, for bouncing, I want to have my bounce height, which I'm going to say is 0.5. Again, we've got different ways we can control how rapidly that bouncing is happening. So we can have our duration for it doing a full cycle. So bounce up, down, return back. Or we could be controlling how many bounces per second. So that would be more referring to as the frequency of the bouncing. So there's different ways of working with this. We can be working with it in terms of frequency or in terms of how long for a cycle, its period or length. Which we want to use is going to vary on the scenario. And it's really down to what allows you to most logically customize the values. So if I want something to be happening at a specific rate, if that's the focus of this is happening at a certain rate, then that's where I would be using a frequency. If we were having something where it was, okay, I want a full bounce to take 2 seconds. If I'm thinking of it from that point of view, then that's where I would use the duration there. So we're going to look at a couple of setups here for this. So let's initially set up, we want to have the bounce period. So how long it takes for a full bounce. So I'm going to say that it takes 1 second. And I know that I'm going to need to keep track of the progress. Bounce progress, which is going to start at 0. So then to update that, so we've got two different functions we could be using. We've got sine and cosine. They will both give you the same rate of bouncing, so you work with them both in the exact same way. The main difference is sine starts at 0. So the output of sine starts at 0, whereas the output of cosine starts at 1. In both cases, it goes between 1 and -1. It does that over the same duration. The only difference is where that starting point is. For something like bouncing, I would normally use sine as a result. So let's have a look at how this works. So on our height offset, and that we can say mathf dot. So there's a lot of math functions are under the mathf thing. So we have sine, and we need to give it an angle. Now you can see that it's saying angle in radians. So there are different ways, different units for angles. In general, on a computer, a lot of the things will work in radians. So they will require radians as an input, or they will give you radians as an output. Radians are not something that, unless you've worked with them a lot, are particularly familiar and an easy unit to immediately jump to. Oh yes, it's exactly this. We're familiar with degrees. We know, okay, a circle has 360 degrees. So we often like working in degrees, but that's not what computers work in. So important sort of set things to know there is, okay, well, we know there is 360 degrees in a circle. There are 2 pi radians in a circle. So radians, you'll see at times it's referring to pi, which is a constant, as opposed to, so it's a specific number, as opposed to the very, very delicious food stuff. Sweet or savory, both delicious. So we need to do a bit of a conversion likely here, and we'll be able to see how we can do that. But what we know is over that 360 degrees, sine and cosine repeat. That is the duration of them. So a full cycle for sine, 360 degrees or 2 pi, same for cosine. And what we're going to be able to see is, so we need to have this value here go from 0 to 2 pi. So that's going to be our bounce progress. So what we would normally do is our bounce progress multiplied by 2 times by mathf dot pi. That's going to give us our height offset, and we can also chuck in our bounce height there. So we're calculating the height offset. Okay, so I need to make sure I'm updating my bounce progress as well. So how I'm going to do that is a little bit different to what we might have seen previously. So I'm adding in delta time, which we've seen that before where we're sort of tracking the current time, but I'm adding in delta time divided by bounce period. Because what I'm doing is I want it so that when bounce progress hits 1, that will actually correspond to bounce period seconds have elapsed. So let's say we had a huge lag and delta time actually was bounce period. So in this case 1 second, 1 second has elapsed, we'd be adding in 1 divided by 1. So bounce progress would immediately go to 100%. So I want to keep it going through that range because I want bounce progress to have it that 0 to 1 corresponds to a full cycle, because that's going to work nicer with our sine and cosine and things like that. So when I'm doing progress values, I usually do this so that they're constrained within that 0 to 1 range. If I want to have this will obviously be able to go over 1. If I wanted to have it nice, which is fine with sine, but might not be fine with stuff. So what I could do in that case is bounce progress, and I wrap all of this in brackets and just modulus it with 1. The modulus ensures that what it will do is it will get the remainder. So bounce progress is always 0 to 1, aka 0 to 100%. So percent is the modulus operator. It returns the remainder. So it ensures we never go over 1. So this is giving us, by dividing by our period, that means we're getting this reliably being 0 to 1 for its initial cycle. And then %1 is going to mean that for future cycles, it's always going 0 to 100%. We don't need to do that for stuff like sine, but there are other things where we might need to do that. So we've got our height offset. Let's take a look then at, we need to remember and store our initial position. So our initial position, oops, that needed to be public. And up here, so our initial position is our transform position. So then we can come here and say our transform position is our initial one plus a new vector 3, 0, height offset 0. Update the height. So let's just see what that looks like. So we know our green cube will be the one that is bouncing, and so it runs. And what we should see, so it's bouncing really rapidly. If we lengthen the period, it's bouncing slower. So bounce period, the larger that is, the longer it takes for a full cycle. And if we pause this and play and just step a couple of frames, we'll see it starts at that initial point there. If I change this to cos, so cosine, then do the same thing, what we'll see is it actually starts up in the air. So we're playing, and we step a frame, and so the first thing it's doing is actually heading back down, because cosine starts at 1 and then goes down, whereas sine starts at 0 and then goes up. So they move at different stages. That's like that. So that's pretty cool. So we've got our cosine happening, or sine, so we can see the different setups that we've got for that, which that gives us a sort of nice sort of setup there with that. Let's look a little bit further of, okay, well, that was using bounce period. What if I wanted to have the frequency? How would I work with that? So what I'm going to do is, that's one where I'm going to actually work with the scale for a change. So what I'm going to do is, this is going to be the pulse frequency. And I'm going to say it pulses at once a second. And then what I'm going to need with this is pulse magnitude, and let's make that 1.5. So I've got my bounce, I've got the progress. I'm going to, and that doesn't need to be public, but I'm also going to have my vector 3 initial scale, and I'm going to have pulse progress. So I'm starting to set up a couple more things here. So, okay, pulse progress. Well, I don't have a, what's its name? I don't have a period with this. So I need to work out how I need to update this. So my pulse progress, so I put in comments here. So pulse progress is always 0 to 1. So again, 0 to 100%. And so I need to think about, so frequency is how many times per second something happens. So if pulse frequency is 1, then progress is 50% at 0.5 seconds, and 100% at 1 second. If pulse frequency is, and this is a good way you can work out these things, you just write it out. If it's on paper, drawing it, whichever works. So if the pulse frequency is 2, then progress is 50% at 0.25 of a second, because we do 2 pulses in a second. And 100% at 0.5 of a second. So, okay, it's got a period that actually is the inverse of the frequency. And this is a way that we can actually work this out. So what we could do is we could say, well, pulse period is 1 divided by the pulse frequency. And then that would allow us to work out stuff. Okay, well, pulse progress then, we know how to do that maths. That's going to be pulse progress plus time dot delta time divided by the pulse period. And again, keeping that in the 0 to 1 range. So we can work out that. And there'll be a way that we can simplify this. I won't do that initially because I want to have it that we've got the logic happening first. So I'm going to store the initial scale, transform local scale. And then to mess with the scale, what I'm going to do is say the transform local scale is going to be my initial scale times by 1 plus my pulse progress times by pulse magnitude. So what that will mean is at 0, so when the progress is 0, the scale is going to be the initial. When pulse progress is 1, then that local scale is going to be our initial times by 1 plus 1 times the magnitude, so times 1 plus 2.5. So it's going to be quite a bit bigger. And in hindsight, I should have chosen smaller values. Update the scale. So let's see what happens with this. You know what, I'm going to leave the scale at what it is, and we can just enjoy the ridiculousness that is about to ensue. So we can see that's a little bit over the top, but the key thing we want to check is that this frequency, what I should find is as this frequency goes down, it pulses slower, which it does, and as it goes up, it becomes unpleasant. So, okay, frequency is working the way we want. We can simplify the maths here. So we can bring this frequency directly down into here. The way we do that is, so this is, the period is 1 divided by. So what we could do is our period, let's take that and change it to this. So we're dividing by 1 divided by something, which is the same as multiplying. So if we're working with a period, a duration over which something happens, we divide delta time by the period. Otherwise, we multiply. So then if we run that, we'll be able to see that it is still working the exact same way that we would want as before. Still making it gigantic as we lower the frequency. Happens less frequently. As we raise it, it increases. So that's the behavior that we want. We want it to be changing correctly based upon whether we're using period or magnitude. That's the effects that we're after there with it. So we've seen a couple of cool things with this, where we can be messing with the sine, cosine using scales. There's a couple of other things that are pretty useful when we've got stuff in a 0 to 1 range. So we could be throwing in an animation curve as well. So this is why I keep things in a 0 to 1 range. It's so helpful for stuff. We could also, if we want to smoothly move between two values, so maybe with the pulse magnitude, I want to maybe have the max and the min of that. So pulse magnitude max, and maybe I want to have a pulse magnitude min that I might make as 1.25. So this gets a bit trickier. I could absolutely work out the maths here, but I don't need to because I've got my 0 to 1 value. So we can use something called a lerp for linear interpolation. So I can lerp, and what I do is I give it the starting value, so the value that corresponds to 0, a progress of 0. I give it the value that corresponds to a progress of 1, and then I give it the progress value, the percentage. So with the lerp, what it will do is whatever this percentage is, this progress, so if that progress is 23.78%, it will go and find the value that is 23.78% between the min and the max. So it makes it really easy to have a smooth blending between stuff. You can lerp also between vectors. There is a vector 3 dot lerp. There's also a vector 2 dot lerp. So easy way of being able to blend between particular ones. And what we'll see is now it'll always start at a slightly larger value. And then I can ramp up that maximum magnitude, and it's just going to smoothly handle that. So lerp is essential anytime you've got that sort of blending between values. Lerp can be incredibly helpful for being able to do that, for having that happen really smoothly. The one thing we do notice with this is it goes up and down, and it snaps back. So it goes up and then it snaps all the way back. We have ways around that. So there is a thing in Unity called Pingpong, where Pingpong is actually an even easier way that we could be setting up this. So what I'm going to do is I'm actually going to turn off pulse progress like that. I'm going to say mathf Pingpong. So we need to give it a value. So in this case, I can just say use whatever the current time is. So time.time. And then I have the period. So because it's the period, I would need to do 1f divided by my pulse frequency. And the key thing is it gives us a value that's between 1 and that length. So if I then set my pulse progress to that, then we can see what will happen. What I'm going to do is, just so we can see how that value changes, I'm going to debug log out the pulse progress. It's going to be a lot of debug logs, but that's okay. But Pingpong gives us different behavior because it goes up and down within that time period we set for it. So let's let it run. So you can see it actually changes smoothly, and we can see the values. So we've got a pulse frequency of 1 and we're going up to 1, but let's make sure this works for values of 2. And it's definitely not behaving the way that we would expect it to for this. The progress here is never getting particularly high, and that's because it's only going up to 0 to 0.5. So when we're working with a frequency, we would need to multiply here. I'm going to comment out pulse progress now. And then this will be going between our 0 to 1 range. If we were using a period, then that multiply would become a divide. So now, smoothly at that, and then if I change the frequency, it moves faster. If I lower the frequency, then it's slower. We do get jumps when we change it here, but that's entirely normal. If I make it that it can go a larger amount, then again, it smoothly moves between those values. So Pingpong will bounce from 0 up to the input value period and back down to 0 once period has elapsed. So, i.e., at 0, it will be 0. At 0.5 times period, it will be 0.5 times period, and at period, it will be 0. And it just keeps looping through that. So Pingpong can be really handy for stuff like that. If we're working with a frequency, we do a divide inside and a multiply outside. If we were working with a period, it would be a multiply inside and a divide outside. So period and frequency, they're just the inverse of each other. So this is version 1 of pulse. Snaps back to 0. Version 2 of the pulse smoothly moves back to 0. We could also use something like an animation curve for achieving this. We could be using sine and cosine for achieving this. So there's different things that we could be using there depending upon what sort of effect we're after with it. So just to recap with stuff. We've looked at a few different bits and pieces here, and it might be different stuff to what you expected. And the reason there is the focus is on what are some bits that you could use and apply. So we saw vectors. Vectors have a direction and they have a magnitude, the length of a vector. So we use vectors for controlling things like positions. We can use them for speed, for launching things, all different setups there. Key thing is they have a direction and they have a magnitude. Oftentimes, that direction, we need to bring it down to be a magnitude of 1 so that we can easily scale it. And we saw with our move to target 1, if we don't normalize the direction, then the farther away we are from the target, the faster we move. And so it moves really rapidly at the beginning and then slows down the closer it gets. Which is not necessarily the behavior we want. So we often normalize things when we're working with stuff like movement. We saw that we can get a vector from one location to another. So to do that, we take where we are heading to. So the thing the vector is pointing at, and we subtract where we are coming from. So to get a vector that goes from point A to point B, we do B minus A. In this case, we're moving to a target. So we get the target's location and we subtract our location. We also saw using our functions like sine and cosine that we can use them to get a repeating pattern because sine and cosine both always move between -1 and 1 and they cycle between that forever. We need to be mindful that oftentimes we're working in radians, which radians are one measurement for angles, whereas we're more familiar with degrees. Unity does have some stuff there for converting between them, but we can also just grab out some helpful things. So we know 360 degrees in a circle, and there's also 2 pi amount of radians in a circle, which Unity does have a thing to define what pi is. So sine, we can use that for doing things like bouncing, so we get a nice cycling there for that. We saw using our modulus operator to keep values constrained within a certain range. And we saw this difference between working with period, so how long something takes, versus frequency of how often it happens. And we saw that period is 1 divided by frequency, or frequency is 1 divided by period. So they're the inverse of each other. And we saw how we could use the ping-pong function, which smoothly bounces between, so it goes up to a value and then goes back down. So we saw how we could use that for working with the pulsing of things. So the big thing that I would say to be doing with all of this is dive in and mess with it. Try changing different things here. Try using Pingpong for adjusting the bouncing. So you could look at using sine or cosine for adjusting the scale. Look at using Pingpong for adjusting the height. We're just bouncing in X here, but you could also be bouncing in the Y, we're just bouncing in Y here, but you could be bouncing in the X and Z axes. Scaling doesn't need to be uniform in every axis. We could be doing one scale in X, a different one in Y, and a different one again in Z. So take these methods and mess with them. Change how and where you're actually applying them. Do multiple versions of move to target, one that normalizes and one that doesn't, so that you could have the two objects race and see how they behave, see which one is going to get there first. But the key thing is experiment with this stuff. Take these, reorganize it, put the pieces together differently, and try, with the goal being of trying to get particular effects, but the main thing being to see what it does. Try applying them to different areas, see what happens, and then try different solutions, try different approaches. Really want to encourage you to be experimenting with this stuff. Make it have ridiculous values, so you've got cubes bouncing that are just taking up the entire world, but experiment with it. Dive in, don't be afraid of the stuff, just embrace it and experiment with it and see what you could create with this stuff. See if you could create a little, pickup item that it's there and it's bouncing up and down, but it's also turning around, because we didn't look at rotation. But have a look at seeing about, you could make it be rotating, you could make it be pulsing in size. Combine these with different things and experiment and start to build up more of an understanding there of what the different pieces will do. Thanks folks, that is all for this video. If you're looking for the project, you'll be able to find it up on GitHub, and I've put a link to that in the description below. If you've got any feedback, any questions, please chuck in a comment. And if you're looking to find ways to support the channel, chucking in a like or subscribing to the channel is always a big help. If you're looking to go further than that, then I do have a Patreon set up, and any support there is super appreciated. And there's a bunch of different things that you'll get as part of being a patron there. And the big thing is, it's going to help me make more cool things like this, which is going to help more people like yourself to be making more games, which is awesome. And that is all for now. Thank you.